Right, so welcome to our first exam review video. In today's video, we're going to be talking about L'Hopital's rule. So we're going to see some examples of how we can solve problems using L'Hopital's rule, and we're also going to kind of break down how we should approach these problems if we see them on the exam. All right, so let's just first talk about how we should approach L'Hopital rule problems. All right, so the first thing that we need to do, and this holds for most of the theorems in mathematics, is we need to understand the statement of the theorem that we're going to use. All right, so if I want to apply L'Hopital's theorem, I should understand what it says. If I want to apply the mean value theorem, I should also understand what it says. All right, so once I have an understanding of L'Hopital's rule, then I need to check that the assumptions hold. In this case, we need to check that we have an indeterminate form, and what form do we have? We're also going to need to check that f and g are differentiable, although in this course, most of those functions that we see, f and g, are going to be differentiable. All right, and then once we check 1 and 2 off, then we can apply the conclusion of L'Hopital's rule. And in this case, the most common types of problems we're going to see, especially when it comes to the final exam, are going to be these 0 over 0 and infinity over infinity type indeterminate forms. And if we do have a problem that isn't 0 over 0 or infinity over infinity, it's typically going to reduce back to one of those cases with just a little bit of algebraic manipulation. All right, so let's see how we can solve some simple L'Hopital rule problems. And as this video progresses, they'll get a little bit harder and a little bit harder. All right, so like I said above, the first thing that we want to do is understand what L'Hopital's rule says. All right, so let's suppose that we have f and g differentiable and that this function g is non-zero, its derivative is non-zero on some open interval I that contains the point A that we're interested in. Right, and this function can potentially be 0 at A, as we'll see here in just a second. All right, so now we also need to suppose that we have one of the two following cases. Either both of the limits as I approach A are 0, or as I approach A, they're either plus or minus infinity. All right, so these are the two things that we're going to mainly check off, is that we have an indeterminate form of 0 over 0 or infinity over infinity. And once I check this, then I can make the conclusion that the limit of their quotient is equal to the limit of the quotient of their derivatives. And this is going to help us solve problems, specifically limits that we may have seen earlier on in the class that we didn't know how to solve using the techniques that we learned then. All right, so let's go ahead then and take a look at our first example. All right, so here I'm taking the limit as x goes to 1 of the natural log of x over x minus 1. And the first thing that we need to do again is check that we have one of these indeterminate forms, either 0 over 0 or infinity over infinity. All right, so let's go ahead and do that. So let's first look at the numerator. And if we recall from the beginning of this course, if I plug in 1 to the natural log, it just outputs 0. So in the numerator, I'm going to get a 0. All right, doing the same thing in the denominator, as I send x towards 1, then I'm going to get 1 minus 1. That's going to give me a 0 over 0. So I do, in fact, have this indeterminate form 0 over 0, and so I can apply L'Hopital's rule. All right, so let's see how we'll do that. So I'm finding the limit as x goes to 1 of the natural log of x over x minus 1. All right, so now that I've checked to make sure the assumptions of L'Hopital's rule hold, really it's just going to be an exercise in taking derivatives. All right, so I need to know how to differentiate the natural log, and I need to know how to differentiate x minus 1. All right, and we've learned how to differentiate these earlier on in the course. So if I take the derivative of natural log is 1 over x, and the derivative of x minus 1 is just 1. So this is going to simplify nicely to the limit as x approaches 1 of 1 over x, right? And now this function 1 over x is continuous at 1. And so as I send x towards 1, using the substitution rule, this is simply going to give us 1. Right, so now we've found the limit of the natural log of x over x minus 1 as x approaches 1 using L'Hopital's rule. And again, these are the standard types of L'Hopital rule problems. You should feel familiar with these whenever you see one on the exam. And now we'll take a look here at a L'Hopital rule problem that gives us an infinity over infinity type indeterminate form. All right, so here I'm taking the limit as x goes to infinity, and I'm looking at e to the x over x squared. All right, so finding the indeterminate form here is a little bit more difficult because we kind of need to think about how these functions behave as I send x to infinity. So I've gone ahead and drawn the graphs for both of these functions, So in the top graph, I have e to the x, and in the bottom graph, I have x squared. Right, now what I'm interested in is as I send x to infinity, so as I travel along the positive x-axis, I want to know what happens to the graph of e to the x. Right, so as I traverse along the positive x-axis, I notice that my function, e to the x, shoots off towards infinity. Right, so that tells me as I send x to infinity, this numerator, e to the x, is going to also go to infinity. Right, and I'm going to do the same thing for x squared. As I traverse the positive x-axis, I notice that my function x squared is also going off to infinity. Right, so I have the indeterminate form, infinity over infinity, which is the second case that we saw in the statement of L'Hopital's rule. All right, so let's go ahead now and just apply L'Hopital's rule. So I'm taking the limit as x goes to infinity of e to the x over x squared, right? And I just need to differentiate the numerator and the denominator. And again, I don't want to get this confused with taking the derivative of the quotient, where you would use the quotient rule. Whenever we're using L'Hopital's rule, we differentiate the numerator and the denominator separately. All right, so let's go ahead and do that. So limit as x goes to infinity, derivative of e to the x, well, that's just e to the x, and the derivative of x squared is 2x. All right, so now let's see if we've made any progress, if we can now solve this limit after applying L'Hopital's rule. All right, so I noticed that in the numerator, taking the derivative of e to the x just gave me an e to the x back. Okay, so as I send x to infinity, let's go back over to our graph. As I traverse along the positive x-axis, well, this function still shoots off to infinity. So I notice in the numerator, I still have something that's going to increase towards infinity. All right, now in the denominator, I no longer have the function x squared. I have a function 2x, right? So that looks maybe something like this here. All right, but regardless of the fact that this function is in the denominator is now 2x, as I traverse along the positive x-axis, well, this guy still goes off to positive infinity. So I'm actually left with, again, an infinity over infinity type indeterminate form. So that means I can then apply L'Hopital's rule one more time, and hopefully when I do that, I get something that I can then solve. All right, so let's go ahead and apply L'Hopital's rule one more time. All right, so I need to differentiate the numerator. Again, that's going to give me e to the x, and differentiating 2x gives me a 2. All right, so now I notice that the limit as x goes to infinity of e to the x over 2 is no longer going to be in an indeterminate form. True, e to the x still goes to infinity, but in this case, the 2 in the denominator does not go to infinity, doesn't go to 0. It doesn't give me one of those indeterminate forms, right? All right, so now in this case, I have a constant in the denominator. I'm going to pull this outside and just use some of our limit rules. I have 1/2 limit as x goes to infinity of e to the x. Now let's try and understand the behavior as I send x to infinity of e to the x. And again, we're going to go back to our graph over here. As I traverse along the positive x-axis and get farther and farther away from the origin, what happens to my function e to the x? It shoots off to infinity. Right, so that tells me the limit as x goes to infinity of e to the x is infinity. Right, so then I have 1/2 times infinity, and of course, that gives me 1/2. Sorry, that gives me infinity. All right, so we can see that moving from the first problem to the second problem, all we had to do here was double check once we use L'Hopital's rule if we could solve our limit. If we get an indeterminate form again, then we just continue to apply L'Hopital's rule. And this is a common method. In some more difficult problems, you'll have to apply L'Hopital's rule twice, 3 times, 4 times, and you'll eventually get something, or hopefully get something that you can then solve like we did here. All right, so let's move on to our next example. in this case, we're going to be taking the limit as x approaches 0 of tangent x minus x over x cubed. All right, and now you may have noticed in the previous problem, we had an x squared in the denominator, and we had to apply L'Hopital's rule twice. So whenever I see a problem like this and I see an x cubed in the denominator, I'm thinking that I'm going to need to apply L'Hopital's rule probably more than one time. But before I get ahead of myself, let's just check to make sure that we actually have one of these indeterminate forms. All right, so now as I send x to 0, I need to understand the behavior of tangent x minus x. All right, so the way that I like to think about this is recalling how we defined tangent. Right, tangent is sine over cosine. As I send x to 0, what happens to sine? Well, it's going to go to 0. Right, so tangent x, this is sine over cosine. And so if I'm looking at the behavior of tangent, it's really like looking at the behavior of a sine and a cosine together. Right, so as x goes to 0, sine of 0 is 0. Right, so that tells me as I send x to 0, tangent's going to go to 0. And then clearly as I send x to 0, this x will also go to 0. So that tells me, after putting everything together, that the numerator is going to go to 0. Right, and of course, if I look at the denominator, as I send x to 0, x cubed goes to 0. All right, so this gives me an indeterminate form of 0 over 0. All right, so that means I can go ahead and apply L'Hopital's rule. So I'm taking the limit as x goes to 0 of tangent x minus x over x cubed. All right, so I need to differentiate the numerator and the denominator. So limit as x goes to 0, I need to recall the derivative of tangent. The derivative of tangent, again, is secant squared x. And then the derivative of x is minus 1. So I pick up the minus 1. And now I need to differentiate the denominator. I get 3x squared. And let's go ahead and double check if we can solve this. If we can't solve this, let's check to see if we have an indeterminate form. All right, so another way that I like to think about secant is just rewriting this as 1 over cosine squared x. And then as I send x to 0, this entire thing goes to 1. Right, so as I send x to 0, secant squared of x is going to go to 0. Sorry, it's going to go to 1. But then 1 minus 1 is going to give me the 0 in the numerator that I'm looking for. All right, and then again, as I send x to 0, 3x squared is definitely going to go to 0. All right, so that gives me the indeterminate form, 0 over 0. And hence I proceed with L'Hopital's rule again. All right, so that means I need to take the derivative of the numerator. So I'm taking the limit as x goes to 0. And now here is where I need to apply some of the rules that we previously learned about derivatives. So I need to take the derivative of secant squared x minus 1. And this constant on the end is not going to do that much, but the secant, we do need to remember how to differentiate this. All right, so recalling the chain rule, this is 2 times secant x, and then multiplying that by the derivative of secant, which is secant times tangent. Right, and then the derivative of minus 1 is 0. All right, and lastly, differentiating the denominator, I get a 6x. All right, and let's rewrite this just to simplify things. I have limit as x goes to 0. The 2 and the 6, that's going to simplify to a 1/3. And then here I have secant squared of x times tangent x over 3x. All right, so now I need to look again. Do I have an indeterminate form, or do I have a limit that I can solve using maybe some other technique that we learned in previous lectures? All right, so I notice that as I send x to 0, this tangent is going to go to 0. So if tangent goes to 0, secant squared of x goes to 1, then the entire numerator is going to go to 0. All right, so this guy here goes to 0. And of course, as I send x to 0, 3x also goes to 0. All right, so that means I then need to apply L'Hopital's rule one more time. The numerator looks a little bit hard to work with. I have a secant squared x times tangent x, and so it looks like I'm going to need to use the product rule. Instead, we can use some of our limit properties and limit rules to try and simplify this limit to make it as easy for us to calculate as possible. And so what we're going to do here is rewrite this using the multiplicative property for limits as the limit as x goes to 0 of secant squared of x over 3 times the limit as x goes to 0 of tangent x over x. All right, so now why am I able to do this? Well, the reason that I'm doing this and pulling the secant squared x over 3 into its own limit is that I can easily calculate this limit, right? What happens as I send x to 0? Well, secant, that's continuous at 0, that's equal to 1. So this first limit here evaluates to 1 over 3. And the second limit is still in an indeterminate form, right? This is going to give me a 0 over 0. And I can apply L'Hopital's rule to determine what this limit is, right? So here, L'Hopital's rule and I want to try and figure out what this limit is equal to. Once I know the second limit, then the total limit at the end of the day is just the first limit times the second limit. All right, so let's go ahead and just take a look at this second limit then. All right, so I'm taking the limit as x goes to 0 of tangent x over x. All right, and like we said, this is a 0 over 0 indeterminate form. So let's go ahead and apply L'Hopital rule. Derivative of tangent is secant squared. Derivative of x is 1, right? And this is usually the end goal whenever I see something in the denominator that looks like x cubed or x to whatever value we're looking at. All right, when I take enough derivatives, eventually it's going to go down to something that is a constant. And the limit as I send x to 0 of secant squared of x is equal to 1. Right, so you've now found the value of this limit here. It is equal to 1. So the final limit evaluates to 1/3 times 1, which is just 1/3.